So this is a discussion for experiment 18, which is on galvanic cells. So the first thing we want to do in this experiment is we want to prepare some mini cells. Okay, so it's going to be a rudimentary cell that we're going to prepare. And they're mini because we're doing it on a small scale. So what we do is we take a piece of filter paper and we're going to cut it so that we have 6 different little petals. It looks like a flower. And on each of those petals, we are going to put our electrolyte solution, because one part of a cell that we need is electrolyte solutions. So I have a silver electrolyte solution, lead 2, zinc 2 plus, iron 2 plus, magnesium 2 plus, and copper 2 plus. So these are all 1 molar solutions that we're going to use to start with. And then another part of a cell that we need is we need electrodes. So on top of each of those electrolyte solutions, we are going to put a piece of metal. So in this case, we would put silver metal on top of the silver ion electrolyte. Here's our lead metal and our zinc metal. And our iron metal, it's actually a coil, so I'm drawing a coil here. So it's a wire that I coil up. And then magnesium is going to go on top of the magnesium 2 plus electrolyte solution. And then finally we have copper, which is going to go on top of the copper 2 plus solution. And that's our brownish colored metal. So the last thing we need for a cell is we need a salt bridge. So these dashed lines represent the salt bridge. So we're going to actually put sodium nitrate drops in between all of the electrodes, the metal pieces that are sitting on top of the electrolytes, and that salt bridge is sodium nitrate. So we're going to use this to create our mini cells. So for part A, we are actually going to make an activity series. And to do this, what we want to do is we want to use copper as our reference. So copper metal is going to be our reference. So we're going to have everything compared to copper. And since it's our reference, we are going to arbitrarily assign it a reduction potential of 0 volts. And we're always going to use it as the anode. So it's going to function as the anode. And the anode is the black lead when we use our voltmeter. And our anode, of course, is our negative electrode. So what we'll do is we'll use our negative lead, which is the black lead, and we'll touch that to copper. And then we'll touch every other metal in this setup. So for example, silver will be red. Okay, so we'll always leave the black on copper, and each other metal will be the red lead. So for this example, I'm doing silver, okay, and it's going to be those leads are attached to our voltmeter, and the voltmeter is going to display a voltage, and it will show 3 decimal places, but this is a rudimentary cell, so we're going to round to the 100th place. Okay, so here in this part A, we may get a negative voltage, and that's okay. So part B is a different story, but here we may get a negative voltage. Okay, so we're always forcing copper to be the anode and each other metal to be the cathode. And we record what the voltage is, either positive or negative. So what we're going to do is make a table of reduction potentials. And I'm going to call them standard reduction potentials since we're using 1 molar solutions. Okay, and so we're going to put the values in for the reduction potentials of each of the metals. So we know our E0 cell equation is it's the E0 reduction potential minus of the cathode, minus the E0 reduction potential of the anode. So our anode is always copper, and we're using it as the reference. So it has a cell potential or reduction potential of 0 volts. We're defining it as 0. And so from this then, we can then say whatever our cell potential is that we measure on our voltmeter, that is the reduction potential of the cathode. And that is the reduction potential of each of those other metals. We're going to rank the metals from the highest to lowest tendency to be oxidized. So based on those reduction potentials, we're going to rank from the highest to the lowest tendency to be oxidized. And in other words, highest to lowest tendency to function as the anode, because the anode is where the oxidation occurs, right? So to function as the anode. So part B is we are going to measure cell potentials, and we want to measure cell potentials for galvanic cells. So what makes it a galvanic cell? Well, galvanic cells have positive voltage readings. So in part B, we want to make sure we have a positive voltage reading. So what we'll do is we will touch our black lead and red lead to metals as indicated in the lab. So for example, let's say we touched our black lead to silver and our red lead to copper. So on the voltmeter, when we do this, we would get a negative voltage. So how do we change it to a positive voltage? We switch the leads. So we would put the red lead on silver and the black lead on copper. And that would give us a positive voltage. And so we want to make sure we write down what the black lead is touching, because that's the anode, and what the red lead is touching, which is the cathode. So we're going to make sure we indicate that in our data table, which I'm going to show you next. Okay, and that's when we get a positive voltage. So positive voltage, we want to know what is our black lead and what is our red lead. So see in our table here, the anode metal is the one that has the black lead touching it. The cathode metal has the red lead touching it when we get our positive voltage. The next column in your table is for the measured E cell, and this is what we measure, so what you'll see in the video, and that's in voltage, right? So that's from the voltmeter that you'll see in the video. So you'll write that down. And then the next two columns, you calculate the E cell. You're going to do it using the data from part 1A. And so to do that, we're going to calculate our cell potential. It's going to be the reduction potential of the cathode minus the reduction potential of the anode. And you'll use your data from part 1A, right? Because you have a table of reduction potentials. So the last column, you're going to do the same thing using the same equation, but in this case, you are going to use the data from your textbook or your notes, right? So you're going to take the reduction potential of the cathode minus the reduction of the potential of the anode from those reduction potentials that you find in your book or your notes. So these last two columns are also in volts, so make sure you indicate your units. So part C is we are going to investigate concentration effects on the voltage. So in parts 1A and 1B, we use standard conditions. We used 1.0 molar solutions for our electrolytes. So our electrolyte solutions were 1.0 molar. For part C, we are changing that for our silver. So our electrolyte solution of our silver plus ion is going to be 0.010 molar. So we're going to make another little cell. We're going to use a piece of filter paper, and we're going to put the electrolyte solutions on it. So in this case, 0.010 molar silver ions. And then we'll use 1.0 molar for our copper 2+. So then on top of the silver, we are going to put our silver metal for our electrode. And then we'll put our piece of copper metal on top of the copper 2+ electrolyte for our other electrode. And of course, we're going to need that salt bridge between them, and that's going to be our sodium nitrate. So then we'll measure the cell potential here. And of course, we want, again, a galvanic cell, so we want to get a positive cell potential. Right, so you want to get a positive voltage. If we don't have a positive voltage, we would switch the leads. So finally, once we have that, we'll go ahead and write that in our lab report. So that will be the measured cell potential that you'll see in the video for that cell that has the 0.01 molar solution of silver. And then you want to calculate what it should be using the Nernst equation. So the Nernst equation is the cell potential is equal to E naught cell minus RT over NF ln of Q. So a few things here. You are going to need to plug in values, of course. So our E naught cell, use the book values to calculate that. So you can calculate that using the reduction potential and subtract the cathode minus the anode from your book values. Then a couple other things is the temperature is 25 degrees C, so convert that to Kelvin for your temperature. And then we have N, which is the number of electrons that are transferred in this reaction for this cell. And then we have some constants. We have R and we have F. So R is the constant 8.314 joules per mole Kelvin. And then F is Faraday's constant 96,485 coulombs per mole. So a couple other things to remember when you're doing this is a volt is a joules per coulomb. And then Q, you're going to have to figure out the reaction quotient Q, right? In order to do that, you need to write the reaction. So you need to write the overall redox reaction, which will give you N, the number of electrons transferred, and it will give you a way to write Q, right? To get the Q expression, which will involve concentrations that you use of silver ion and copper 2+ ion as your electrolyte solutions. So once you plug all that in, you can solve for your E cell. Okay, so you're solving for your E cell in this part.